Hey guys, so in this video we're going to review the heating and cooling curve. First thing we're going to look at is the heating curve, and in this curve we see that heat is entering, which we call endothermic, so endo, entering. If we notice along the bottom, we have as time is increasing, our temperature is increasing, and temperature we also relate to as our average kinetic energy. In this first incline here, we just have our solid phase. In this area, we have our average kinetic energy. Our temperature is increasing, so there's a change in our average kinetic energy, but there is no change in our potential energy. The point when one of our solid particles turns into a liquid particle is called the melting point. And after this melting point, we have this plateau area, which we call a phase change. And in this phase change area, we have the solid particles are turning into liquid particles. We call this liquefy or melt. In this area, again, we have a phase change, so P for phase change, P for plateau, P for potential energy changes. In this area, our potential energy is increasing. In the next incline, we have our liquid phase, and in this area, our average kinetic energy is increasing. Our potential energy is not changing. The point when one of our liquid particles turns into a gas particle is called our boiling point. Again, after this boiling point, we have a phase change, and our liquid particles are turning into gas particles. And in this phase change area, we call this evaporate, boil, or vaporize. Again, there is a change in potential energy. There is no change in average kinetic energy. And lastly, we have our gas phase, and our temperature is increasing here, and our potential energy has no change. Next, we have our cooling curve, if you notice, is the opposite of our heating curve. So heat is exiting the system, which we call exothermic. So think exo, exiting. We start with our gas phase. And in this area, our temperature or our average kinetic energy is decreasing. Our potential energy has no change. The point when one of our gas particles turns into a liquid particle, we call our condensation point. And after this point, we have a phase change. And in this phase change, where we go from a gas to liquid, we can call this condensing. Again, there is a change in our potential energy. The potential energy is decreasing, and there is no change in our average kinetic energy. And our next incline, we have a liquid phase. And in this liquid phase, again, our average kinetic energy is decreasing. There is no change in potential energy. The point where one of our liquid particles turns into a solid, we call our freezing point. And after this point, we have a phase change where we convert liquid particles into solid particles. And in this phase change, we can call this solidify, crystallize, or freeze. After this area, we have one last incline, and we have our solid phase, and this is where our temperature, our average kinetic energy decreases, and there is no change in potential energy. So in the last part of this video, we're going to do a little recap on our particle diagrams for solid, liquid, and gas. So for a solid, we have this particle diagram where there is a definite volume and definite shape. There is a geometric repetitive pattern, and we have a crystalline structure. It is important when you draw your solid particle diagram that you do not have the particles touching the side of the container. We want to see that it is rigid and that we have this geometric pattern. Next up is liquid. The liquid phase has a definite volume. It does not have a definite shape, and the particles have a random pattern. If you notice, the particles take the bottom of the container and fill it in. Lastly, we have our gas phase, and in this particle diagram, we have no definite shape, no definite volume, and these particles uniformly fill the container. And again, this is a closed system, a closed container. If you notice, the particles are a lot more spread out, and they fill that container completely.